Hello, people. All right, it's time for enzymes and catalysis. We spent a little bit of time talking about enzyme binding and specificity, and now it's time to move on to the thing that makes enzymes different from the other proteins, is that they convert a substrate into a different chemical by breaking bonds, making bonds, all sorts of things. Okay, so after this video, you should be able to define some key vocab terms, describe Michaelis-Menten kinetics, determine KCAT, KM, KCAT, and KM. I highly suggest you get a calculator out. There will be some math in this video, and we'll do a pretty long example at the end. And then analyze the meaning of these three values, and then predict the effect of a mutation on Km and or KCAT, and of course KCAT over Km. Lots of things to start with K today, lots of things to start with M today, so I hope that you're ready, and get started. Here we go. All right, so remember, the second biochemical requirement for life is the ability to catalyze reactions selectively and efficiently. Okay, and this being biochemistry, we want to be able to quantify what selectivity and efficiency mean. So one way to describe how selective an enzyme is and how efficient an enzyme is to put numbers on them and then to compare the numbers. So that's what we're going to do. Biochemists can quantify things with respect to enzyme activity with respect to substrate concentration. That is an S. That is an S. Life. With respect to substrate concentration, pH, temperature, and inhibitor concentration. This video is going to only be about quantifying selectivity and efficiency of an enzyme with respect to substrate concentration, and we will get to temperature, pH, and inhibitors. That will be almost all the other days of enzymes that we have. How fun, how exciting, how lucky are you? Okay. So if you can recall our basic equation where we have E, enzyme, and substrate bind together with high specificity or selectivity. And then today we're going to talk about how quantify-wise we can get from the binding event to the catalytic event where substrate is turned over into product. But in order to do that, we're going to make a couple of assumptions. We're going to assume that as we increase substrate concentration, so in this diagram it's moving to the right here, as we increase substrate concentration, the enzymes will become saturated. With substrate. I'm just going to put S, okay? So as we increase substrate concentration, enzymes will become saturated with substrate. So what you can see over here is all the little Pac-Man enzymes at low substrate concentration. It looks like only one is bound to its substrate. We start increasing substrate concentration, and oh look, now we have 3. And at high substrate concentration, we assume that almost all, if not all, enzymes will be bound to substrate. That's one of our main assumptions. All right, and this enzyme kinetics can be described in what's called Michaelis-Menten kinetics. So the assumption that at high substrate concentration, all the enzymes will be bound with substrate is one of the assumptions. There are many of them. We're not going to go through all the assumptions. We're also not going to derive the equation because I don't think it's actually useful. It's more useful for you to be able to interpret a graph. So here we go. Michaelis-Menten kinetics. Some of this should look very, very familiar. So Michaelis-Menten kinetic graph will have substrate concentration down here in some units of molarity. Could be micromolar, could be nanomolar, could be picomolar, could be millimolar. Who knows? It's just molarity. And then over here on the y-axis, we have the funky V0. Now this is called initial velocity. It has units of moles per second. That's its units, moles per second. Please don't forget that. It's not just per second, it's moles per second. And it represents the initial velocity right after the enzyme and substrate are mixed. Okay? The Michaelis-Menten graph here is hyperbolic. Ooh, have you seen a hyperbolic curve before? Yes, I hope you have. It doesn't have that little lip at the end. That's not there. All right, it's hyperbolic, so it comes up, rises, and up at the plateau there, this plateau here represents, oops, I wanted a different color. Okay, this plateau right here represents at high substrate concentration, all of the enzymes are bound. Okay, this value where it plateaus off right here on the x-axis is called V max, or the maximum velocity. So if you were to find the plateau and then figure out where that is on the x-axis, that is V max. Again, V max will be in some units of molar per second or moles per second. Okay, and the most important number that we get from this graph, come on, go by colors, is Km. Now Km is when you find the Vmax, then you find half of the Vmax, figure out where it hits the hyperbolic curve, and then drop it down, and that value right there on the x-axis is Km. Km is the substrate concentration at 1/2 of Vmax. Okay, so I'm just going to say that one more time. So Km is substrate concentration at 1/2 Vmax. So first, you have to figure out what your Vmax is, and that's going to be here. And then you'll find half of that. Drag this over to the curve, and then you've got to drop it down to the x-axis to find Km. Km is called the Michaelis constant. Okay, this should be feel very similar to how we found Kd, only if you remember with Kd, what we had is ligand concentration. Remember, ligands are different than substrates, same units though. We had percent binding over here, and the range was 0 to 1, and we would find half binding, half percent bound, and that would be our Kd. Okay, so Km, just to remind you that Km and Kd are different, because we're working with Km, we're working with a protein that's an enzyme, so the thing that it binds gets turned over into a whole different product. Whereas a ligand, it comes in and it comes out, and it's still the same when it comes out. Okay, so Km, because of its similarity to Kd, is a measure of how tightly the enzyme binds to the substrate. And I want to remind you that Kd is the measure for binding. And we're going to do a little bit of math to show you that Kd is the measure for binding, and for enzymes we use Km as a measure for binding, not the measure, but it is a measure. And just like with KD, we have certain values that indicate weak binding versus strong binding. So a high Km, such as, I don't know, 1 micromolar, indicates weak binding. And a low Km, the lower the Km, the stronger the binding. Such as 1, how about nanomolar, indicates strong binding. Okay, same thing with KD, the lower the value, the stronger the interaction. Again, that correlates right to delta G, because the stronger the interaction, the more non-covalent forces or bonds that are being made between the substrate and the enzyme, so the lower the delta G, and all that good fun stuff. Okay, I have to do this like brief shout out to Maude Menten. Maude Menten is one half of the Michaelis-Menten team duo. Why am I doing this? Because I want you to add a famous female scientist to your repertoire of your famous scientists that you know. And Maude is probably my absolute favorite. One, because her name is Maude Menten, and like, how cool is that name? But 2, she was pretty much a badass, and even like in today's standards, she would still be totally amazing. So she was one of the first women in Canada to receive a medical doctorate, but it turns out they wouldn't let her practice medicine because, if you'll notice, the time period with which she lived. So she practiced medicine a little bit in the U.S., but then she went over to Germany, and she worked as a researcher with Lenore Michaelis, and that's when they developed the Michaelis-Menten equation, and she did a whole bunch of other stuff. Where is it? Oh yeah, so she did a whole bunch of other stuff: hemoglobin, kidney functions, blood sugar. She had a master's degree in physiology. Look at this. She authored 70 academic papers. Crazy. Okay, and if that wasn't enough, she was a painter, spoke 6 languages, mountain climber, went on an Arctic exhibition. Okay, that's awesome. Played the clarinet, astronomy. Anyways, she was pretty amazing. So Maude Menten, one half of the Michaelis-Menten, and she made a whole bunch of other discoveries that we actually still use in biochemistry and physiology today as well. So Maude Menten, badass chemistry lady, biochemistry lady. Okay, getting back to it. Okay, so enzyme kinetics versus protein binding. I kind of alluded to how we use Km as a measure for binding, whereas Kd is the measure. So I want to just give you a little bit mathematical logic behind this. So here is our general equation, E plus S. This is the binding step right here. And if you'll notice, that equation is identical to the binding equation, where P is protein, L is ligand, and PL is our protein ligand. The rates, we have our on rate, we have our off rate. But the first part of this equation essentially looks the same. And again, if you'll remember, one of the ways that KD can be quantified is the off over the on rate. Okay? Now Km, if you look at its rates, this is the equation for it. Please don't memorize this. You don't need to memorize this. But in order to estimate Km as a measure of KD, we make an assumption that KCAT is way, 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 way smaller than K minus 1, or the off rate. Or in other words, the catalytic rate is rate limiting. Or it's just super, super, super small. And if we do that, then we can say that KCAT is negligible. All right, and if we say that KCAT is negligible because it's so much smaller than the off rate, then Km essentially becomes K minus 1 over K1, which, if you'll notice, is this exact same equation. So that's why we say Km is a measure of binding. It is not the measure of binding. This is the measure of binding. But if we make this assumption, if we make this approximation, then Km is an indication of binding. Kind of cool, huh? All right, so Km is our indication of binding. Next, we're going to talk about KCAT. All right, so KCAT is another quantity used to characterize enzyme-substrate interactions. So KCAT is also known as the turnover number. Put this in quotes. This is a quote. Turnover number. It's also known as the catalytic constant. Catalytic constant. Okay, its equation, so KCAT is equal to Vmax over enzyme concentration. Okay, you need to memorize this. I will not give you this on an exam. And what it is, in other words, is KCAT is the number of catalytic cycles by each active site per second. So if you'll notice, all these KCAT values have per second, per second, per second. For KCAT, the bigger the number, the better. Okay? So it's just kind of the opposite of Km. So here, the bigger the number, the better or more efficient. Basically what it's saying is that it's basically how quickly a substrate, when it enters the active site, is turned over into product. Okay, so how quickly the substrate is turned over into product is the turnover number, and the faster the enzyme is at this, the better the enzyme. So bigger numbers are better here. All right, and then the number that biochemists really want is to put them together. Okay, so the number that biochemists really want is this value called KCAT over Km. And the reason for that is this part right here is selectivity or specificity. And this part right here is efficiency. And of course we want to know both of these two values together. So this KCAT over Km is also called catalytic efficiency. Okay, and it's always in units of per molar per second, and the bigger number, the better here. So the highest observed values is somewhere on the order of 10 to the 8th, 10 to the positive 8, to 10 to the 9th per molar per second. And the reason for that is that if you have an enzyme like fumarase right here, has a KCAT over Km of 10 to the 8th, we call this catalytically perfect. And this enzyme is diffusion controlled. All right, so what do I mean by that? If you remember the rate of diffusion, 2.4 times 10 to the 8th per molar per second, this is the upper limit. Essentially, an enzyme cannot be any more efficient than a substrate can diffuse to it. So if this is the rate of diffusion, you can't have an enzyme be better or faster than the rate of diffusion. Now, with the caveat here, of course, that this 10 to the minus 9 is greater than the rate of diffusion. These are measured outside of the cell in test tubes. So in those circumstances, you might be able to get something that's a little bit better. But any enzyme that has a 10 to the 8th, 10 to the 9th per molar per second, always per molar per second, not micromolar, not millimolar, is said to be catalytically perfect and is diffusion controlled. Okay, so how can this information be used? If you remember in the last video, I talked about there are these binding sites and the catalytic sites, and in these there are specific residues. So all of these right here in the blue, there's a whole bunch of residues there, and in red there's a whole bunch of residues there. Well, we can use point mutations to figure out which ones are binding residues and which ones are catalytic residues, because I'm telling you, you won't know coming out the gates. All right, so wild type is the regular one, and this is real data. How do I know it's real data? Because it's my data. Whoop. Okay. Shout out. All right, so wild type, I'm not going to tell you what the substrate of the enzyme is, but it was measured, the Km was measured to be 180 micromolar, plus or minus 2, and the KCAT is 3,500 plus or minus 100 per second. Now, I suspect that this histidine is important is part of the active site. I don't know if it's binding. I don't know if it's important for binding or catalysis, but I mutate it to an alanine. That's the most common mutation to make. And what I see is that the Km goes up a little bit, and the KCAT goes down by a lot. So remember, the bigger the KCAT, the better. So if you have such a dramatic decrease in KCAT, then this is likely a catalytic residue. Okay? And this one right here, because again, the lower the Km, the better, when this one increases, this is likely to be a binding as well. So some residues in the active site can be both, could be both catalytic and binding. So both the Km and the KCAT changed beyond the standard deviation here. So both, this is a binding, so histidine 64 is both binding and catalytic, important for both. Now I've got an arginine in there because I can see it, I can solve the structure, whatnot. I mutate it to an alanine, and I want to see what happens. Well, it turns out nothing really happens to the Km, and nothing really happens to the KCAT, so it's neither. It's not important in binding or catalysis. It's probably just one of these structural support, one of these gray area ones. And then I see an aspartate, and I mutate that one to alanine and see what is the effect. Well, Km, went way, way up, so it's definitely a binding residue. And KCAT did not do anything. So this aspartate is only important for binding. So that's one way that this information can be used. Now, next we're going to do an example where I'm going to walk you through how to determine KCAT, Km, catalytic efficiency, and so on and so forth. So if you don't want to watch the example, then you're all done with the video. But if you do want to watch the example, strongly suggest you go find yourself a calculator and come on back. Okay, so I found this graph on our good friend, the internet. So we're going to work through this as best as we can. So what I want you to do is determine the Km, KCAT, catalytic efficiency, and then I've given you some extra information. The absorbance of the enzyme was measured at 280 nanometers to be 0.75. And it has an extinction coefficient of 10,000 per molar per centimeter. All right, so let's start with the Km. I gotta move this over a little bit. My little keys are... Okay, so remember our Km. We have to find the Vmax. So let's say our Vmax is about 0.6. So I'll just collect that information. I might as well. Vmax 0.6. Let's see. We are in, wow, picomolar per second. That's interesting. Picomolar per second, which is 0.6 times 10 to the minus 12 molar per second. My suggestion is to always move your units to molar, big M, and seconds. Sometimes the values will be in per minute, sometimes they'll be micro. Just my suggestion is get to the big M and little s just right away. All right, so that's Vmax. Km, we want to go half of that, drag it over to the line, and then drag it down to the x-axis. And I will approximate that to be, I don't know, 3 micromolar. Again, I always move right into molarity, so 3 times 10 to the minus 6 m. All right, so I've got my Km, check, did it. And then my KCAT, one of the equations that you need to have memorized is Vmax over enzyme concentration. Now I have Vmax, so this is the Vmax that will go here. Now E, I've given you cryptic information on how to find E. Now this information requires you to remember our good friend Beer-Lambert's law. So Beer's law is absorbance equals the extinction coefficient or molar absorptivity, path length, and concentration. So I have given you E, that's this value right here, or this funky epsilon. I've given you absorbance. Remember, absorbance is unitless, so this is 0.75 equals 10,000 per molar per centimeter. Okay, path length, this is the width of the cuvette, which is typically 1 centimeter. You can always just assume 1 centimeter. And then that leaves you with C, which is concentration. So what you'll notice is that my centimeters will cancel out, and the only units left over will be molarity. So I do the math here, divide 0.75 by 10,000, and my concentration, hopefully you get the same number as me. And that number is 7.5 times 10 to the minus 5, big M. All right, so for my KCAT, I can plug in my Vmax, 0.6 times 10 to the minus 12 molar per second, and that will be divided by 7.5 times 10 to the minus 5 molar, and do the math, and you'll get a number, which, did I calculate it out? Where did it go? Hold on, I gotta calculate it. Okay, we got a super tiny number, 8 times 10 to the minus 9 seconds to the minus 1 or per second. This is a really, really, really small KCAT, so already I'm thinking like this enzyme kind of sucks. So I have my KCAT. Now I have my, so here's my KCAT. I have my Km. And next I need my catalytic efficiency, which if you'll remember, catalytic efficiency is just the combination of the two. KCAT over Km, again, you need to memorize that because I will not give you that. And that's 8 times 10 to the minus 9 seconds to the minus 1. And then that should be something that's per molar, so 3 times 10 to the minus 6 molar. And I'm going to have to calculate that. Okay, I get 2.67 times 10 to the minus 3 per molar per second, and this enzyme is definitely not catalytically perfect. It is way, way far away from 10 to the 8th. In fact, this enzyme this is rough. So I made up this value for enzyme concentration, so I don't really know what enzyme concentration they did here. I'm hoping that the enzyme in reality is a lot better than this, otherwise that'd be really sad. But hopefully you can also see that NAD+, that is their substrate. Rate of ligation, so they're trying to fuse, the enzyme fuses two things together. What it is, I don't know. But anyway, so that's my example of how to find KCAT, KM, and catalytic efficiency using a little bit of cryptic knowledge on how you would in the laboratory find enzyme concentration using Beer's law. And that's all I have for you. Happy math, happy life. I'll see you in class.